Hello, Jack. My name's Adam Millar. I'm a colleague of Chris Roberts at the Canterbury School, and we've been corresponding a little bit about your proof of Goldbach's conjecture. So thanks for sending your updated proof. I think there are still some problems with it, or at least things that I don't quite see yet. So I'm going to go through what I think I understand and tell you where I think there might be a problem, and then we can talk a bit more about it. So I might be a bit off with my index numbers or the order that they happen in, like P or K, but I'll try to be as consistent about that as I can. So you've built this set F as a union of unions where the first index is K primes, and the second is J. And so you first pick your first index, which for me is my vertical axis here. You start at 2 and you count up the naturals. So this is K, the enumeration of the first dimension, and you assign to it the nth prime, the kth prime rather. So that's this dimension. And then after finding all of those unions, you do an index over J for the second dimension, which is J, which is my horizontal axis here for my table of evens. So yeah, your set is a big grid where the coordinates are the nth prime, the nth prime, comma, the mth prime, and the cell or the element with that pair of indices is P of n plus Q of n. So each position in this grid is I or K comma J, which will be P of n plus Q of m. So K goes with n, J goes with n. And you want to prove by induction, you have the base case, 8's in there, there it is. It's 5 and 3, so we're good for our base case because Goldbach's conjecture says greater than 6. 6 is in there. And we want to say that given an arbitrary E, even number E, if it is in this set, then the next even, E plus 2, is also in this set F that we have built. And if we can show that inductive hypothesis, then we know that F contains only even numbers because every non-2 prime is odd, and so the sum of two odds is odd. So every element in here is an even number. We want to show, so we know that this contains only evens, and we want to show that if something's even, then it must be in here by induction, as I just described. So we can see, again, the general idea of your proof is to say, okay, take an arbitrary E that is in the set. And we need to show for induction that E plus 2 must also be in the set. So I illustrated an example to try to see what's going on. So I said, if it's 22, then we need to show that 24 is in there. And what you said, if I follow your explanation correctly, is you're basically saying, well, it's either going to be in the same row over one column or in the same column down one row. It's going to be kind of adjacent, very close, the next even. And what I'm concerned about is that statement of the inductive hypothesis is a bit too general, because with that statement, I found a counterexample to that general statement. So if we need to go further, we have to tighten up, because look, 14, look, suppose I have 14. It is some it is some E, it's some Pn plus Pm. Well, one place that 14 appears is here at k equals 4, j equals 4. So it is P4 plus Q4. And so that's this 14 right here. So neither Pn plus 1 plus Qm, this number, so this is one row down, neither that number nor this number is 16, which it would have to be for the inductive hypothesis to follow. So as stated, I believe the inductive hypothesis cannot be proved in generality. Now, it turns out that 14 does appear in this grid, right? With neighbors that are the next even. But again, as stated, we haven't been, again, I believe the counterexample I've illustrated for this 14 right here shows that we have to at least consider additional cases when we say take arbitrary E in F. When we begin for induction, so we're doing induction over the even numbers, evens in our set F. So let E in F be arbitrary. We want to show that given E is in there, that E plus 2 must also be in there. And all we know about E is that given the definition of F the way it was constructed, E must be equal to some Pn plus Qm. But it looks like, depending on, so elements can appear in multiple places, and with the example of 14, it matters which one we pick. So we have to split some cases here, at least, where it's like, well, does n equal m? Because it looks like in some cases, if they do, this won't follow, like for 14. And you need to say something like, well, if they're equal, then don't worry, this will appear somewhere else. Oh, this should be a 20. Because, for example, there will be like 22, I believe, will not appear anywhere else. Yeah, 22 will not, hold on. Sorry, I'll think about that later. Either way, we need to make some case for saying, well, if they're equal, if it's on the diagonal, then it will appear somewhere else. That's not obvious to me. And then conversely, if they aren't equal, then either the row neighbor or the column neighbor will be E plus 2. I don't know, maybe we can set up a video call. I know you're down in Florida. At least we're in the same time zone. But yeah, if we could have like a video call or something, I could collaborate on a whiteboard or something. If there are any, before I started recording, I tried to make sure that I felt pretty confident about what you were trying to say. And it's definitely on the right track, like the overall structure of the proof of saying I have constructed a set of even numbers defined in terms of their sums, the sums of primes. And now I need to show that that set not only contains even numbers, it contains every even number. That seems like sound methodology I just don't think that the inductive hypothesis as stated follows. So yeah, I mean, look forward to seeing if you can change my mind. And thanks for watching. I guess I know it was a long one.